Welcome to the Explainer. Today we're unpacking one of the absolutely most fundamental mysteries in all of quantum theory, Compton scattering. Okay, let's dive into this, because we're going to explore how light, something we normally think of as just a continuous, flowing wave, can actually behave like tiny, super-energetic projectile.
So, is light just a wave, or is it something more? Think of this explainer like a subatomic detective story. For the longest time, classical physics was entirely comfortable treating light purely as a wave. It ripples through space, it bends, it flows. But as scientists started peering deeper into the subatomic world, well, that neat little explanation began to fracture. We're tracking down the true nature of light right now, and the clues? They're all hiding at the microscopic level.
Section 1. The Mystery of Light.
For centuries, classical wave theory was the undisputed champion of physics. But when it came to specific, high-energy collisions, it just completely fell apart. It literally could not explain the phenomenon we were observing in the lab. And this brilliantly illustrates the paradigm shift, because Arthur Compton's groundbreaking discovery supported the photon model instead. This proposed that light isn't just this continuous wave, but is actually made up of individual, distinct packets of energy called photons.
Section 2. The Quantum Collision.
I want you to imagine a high-speed game of billiards, but played with the fundamental building blocks of the universe. In step 1, a high-energy photon speeds in and directly strikes the stationary electron. Boom! Step 2. Just like a cue ball, the photon transfers some of its energy right into the electron. Step 3, the electron is knocked away. And finally, step 4, because the photon gave up that energy, it recoils with less energy than it started with, and crucially, its wavelength actually increases. It literally stretches out. The contrast before and after the collision is exactly what proved the theory. Look at it before the collision. The incoming photon has super high energy and a tightly packed, really short wavelength. But after the crash, having lost energy to the electron, its wavelength stretches out and becomes longer. The light itself has been fundamentally altered by a physical impact. A traditional wave shouldn't behave like a solid object in a crash, right? But a particle definitely does. Now, this physical transformation is called the Compton shift. Let's define that clearly. It is the increase in wavelength of X-rays or photons after colliding with electrons. When physicists talk about the Compton shift, they are referring to this exact loss of energy and the stretching of the wavelength that happens during these massive subatomic impacts. And this brings us to an absolutely massive realization. To quote the finding, light behaves like a particle with momentum. Think about that for a second. Momentum is a property of mass and motion. It's what makes a heavy truck so much harder to stop than a bicycle. Proving that light can physically hit an electron, transfer energy, and bounce off changed? No way around it. That means light acts exactly like a physical particle carrying momentum. Section 3. The Compton shift equation. And don't worry, we are going to break these numbers down simply and logically. Here is the elegant mathematical proof of the whole phenomenon. Now, what's really interesting about this slide is how perfectly it predicts exactly how much the wavelength of the photon will stretch out after the impact. The formula is delta lambda equals h divided by the mass of the electron times the speed of light, all multiplied by 1 minus the cosine of theta. Let's map those variables out so we see exactly what forces are at play here. Delta lambda, that is our total change in wavelength. We factor in Planck's constant h, the mass of the struck electron, m sub e, and c, the speed of light. Finally, theta gives us the scattering angle. That's basically the trajectory of the ricochet after the crash. You plug in the constants, measure the angle, and the quantum math just works out perfectly, every single time.
Now, a quick note here. You aren't going to see this happen when you turn on a standard light bulb or a regular flashlight. The Compton shift really requires a highly energetic collision to even be measurable. That's why this phenomenon happens mainly with high-energy X-rays and gamma rays, which have very short wavelengths. Those are the specific, intense conditions needed for these subatomic crashes to actually occur in the real world.
Section 4. Real-world quantum applications. Let's zoom out from the microscopic math and see why this actually matters to us.
Because we understand how these high-energy photons interact with electrons, we've been able to unlock some absolutely incredible technologies. First, medical imaging relies heavily on X-ray scattering to see inside the human body safely and accurately. Then there's radiation physics, which uses these precise energy transfer models for everything from cancer treatments to running nuclear power plants. And in astronomy and space science, it allows researchers to decode gamma rays shooting across the universe from distant galaxies, black holes, and supernovas.
This phenomenon gave the scientific community undeniable evidence for two huge truths. So the crucial point is this. First, light has both wave and particle properties simultaneously. It's a dual nature. Second, photons carry momentum. They aren't just empty ripples moving through space. They actually have physical weight in how they interact with matter on a microscopic level.
Ultimately, we are left with this definitive truth. Compton scattering proves that light behaves like particles carrying energy and momentum. It is a profound, fundamental reality that forces us to accept that our universe is just far more beautifully complex than classical physics ever imagined.
So I'll leave you with this. If something as seemingly simple and everyday as light can successfully hide a dual nature for centuries, what else in our universe hides a dual nature? What other incredible mysteries are just waiting to be uncovered right now in the subatomic world?